כן, אני שומע, דניאל. We have with us today Dr. Daniel Hartmann from the Unit of Safety Engineering and Management at the Ben-Gurion University. Daniel did his PhD studies at the Institute of Earth Sciences in Aarhus University at Denmark, then did a postdoctoral stint in the Ben-Gurion University at Sde Boker and at the main campus, before going to teach at the Ahwa College and then coming back to teach at the Safety and Engineering Management Unit at Ben-Gurion. Daniel has very diverse research interests spreading through water risks and safety management and disaster management, very interdisciplinary approach. We will hear today his talk about a basic, he will introduce the basic parts of STAMP, System Theoretical Accident Model and Processes. I guess it will be with most emphasis related to industrial processes. And Daniel, the screen is yours.
Okay, thank you, Eran. Hi, everybody. I have my brain has to switch from Hebrew to English, so at the beginning it will be slow. I will be able in this 45 minutes talk is just to introduce you some ideas about what we call, let's say over the last 20 something years, safety sciences. Well, we have at our university a unit for second degree, master's degree, safety management and engineering, but we don't do safety science, unfortunately, at our unit. But in the world is doing safety science, and the world needs to do safety science. And safety scientists are not safety engineers, but actually in each discipline, in each area, there are people who specialize in safety. And when I say safety, I will stress it from the beginning. When we say safety, safety and security is one topic. Yes, we don't separate them. Security is just a special case of safety in our view. And in this talk, I will first introduce to you my motivation. Yes, why do I care trying to talk and to present the ideas about safety science, especially the modern ones? Yes, and you will find out that if you know something about safety, you know things that are about 40, 50, 60, 70, or even 100 years old, and they are maybe too old for our modern age. So I have a motivation, yes? And we have always to remember the Thanksgiving turkey, yes? Was born, was a little one, and then it's growing and growing. And it takes about 3 years for a turkey to become a full developed turkey. But he finds himself on a platter in a Thanksgiving holidays. So we have to remember it, that safety is thinking before you act, yes? And in Hebrew, we have a very good saying, Sof ma'aseh b'machshava tchila. So we have to know what we are doing if we want to be safe. And safety has different aspects. One of them is, of course, human lives, yes? And we all remember the disaster, the Carmel disaster. 44 people died in a very complex accident or disaster because of so many people. And we paid with blood for unsafe behavior, let's call it this way. But safety has also a very strong financial aspect, yes? And this is a very famous, or well, for us, it's a very famous curves where we can see that if we look at the system life cycle and we are thinking in systems, yes, following what discipline like system engineering is dealing with, yes? So we are interested in the life cycle of a system. And our ability to impact cost and performance related to safety, but also to other topics, is from the beginning, if we are thinking and we are aware of ways to do better safety, yes, then the impact is very strong. And the cost of design change, so if we have a new concept, we are writing down the requirement for this new concept, we're starting with the early design, we are living in so-called solution-free design environment, and we think from the beginning with the right tools, right models about safety, we can impact it very strongly, the cost of the system, yes? And if we wait, yes, and we can have all along the life cycle, we have accidents, and in a few slides I will explain what I see as accident, yes? Then accidents are not only during the operation, they can be, a concept can be wrong, the requirement can be wrong, the design can be with flaws and so on, yes? So if we wait to have accidents in the operation and then we want to change something, it costs a lot of money or even can cause a company or the system to break down, yes, to get kaput. Okay, so if safety is too expensive, because many managers say, oh, it's so expensive safety, yeah, then we have a saying, then try an accident. It's very easy to try an accident to see where the costs are more heavy. So therefore, the approach that I am using and that caught my eyes, and I think that it's a good approach, is if we treat safety in the early stages of the design, and we actually are interested in safety guided design. Yes, so when we design a new system, it doesn't matter, is it a process industry, is it aviation, is it transportation, it's medicine, whatever. Our corona problem, if we design safety into the system from the beginning, then we will save life and we'll also save money. Okay, now I have to, I was really thinking much about it. I do want to give you some very short introduction to safety science. Very short, what do I mean by saying safety science? So safety science starts from the top. So if we want really safety, the management, the regulation, the legislation, everything has to be embedded in thinking about safety. Now, it's through the literature, we can divide different organizations and even different countries according to this safety culture ladder. As again, I have here in the presentation many slides that only one slide could be followed by a lecture, yes? So safety culture, you see the lowest level are organizations or countries that are pathological. They don't care about safety, yes? Then the second level would be reactive, yes? Organizations that react to something and try to, in a way, maybe to fix it or whatever. The third level is calculative, where organizations try to comply to the regulation, to standards, to legislation, and so on. And the two upper, they are much more advanced. Unfortunately, I think, I don't know if someone in the world tried to categorize organization according to this ladder, but I would say the 99% of organizations are within this central part of the part of the ladder. Yes, there are almost no organizations that can call themselves proactive or generative, and to be so, they have to change paradigms, the way we think. And also, when I talk to you, my intention is to change the way you look at safety, at the paradigm of safety, and so on. Yes. If you don't do it, you have no modern safety. Okay, so it starts with us as human beings. Yes, human beings have a lot of biases. I hope, or I think most of you heard about Daniel Kahneman. Daniel Kahneman has a list of, I don't know, about 20, more than 20 biases that we human beings have. Yes, and one of the biases, I don't know if Kahneman talked about it, but this is a very severe bias, is that we are born to think linear. Yes, and I will explain in the next slides why. So we are born, our evolution brought us to think linear, and we are event-oriented, we have event-oriented thinking. But for the modern world that we live in, which is a very complex world, we need a different way of thinking, yes, system thinking. And system thinking has in it also the way to think in loops, in loops, yes, control loops with feedbacks and so on. And unfortunately, I'm teaching, well, I'm already teaching at the universities 40 years. In engineering sciences, you do not teach your students to think in system thinking, yes? There are extra, there's an extra discipline called system dynamics, system thinking, and we don't find it at our university. In many universities, we don't find it. So please, one of the first thing that I would like you to remember is that the linear or event-oriented thinking is not suitable for modern life, and especially not for safety. You have to learn to think in a system thinking way. The second topic is information. We cannot do safety without knowing enough about what we are going to care about its safety. We are human beings, Homo sapiens sapiens, but humanoids exist now for about 2 or 3 million years, even longer, yes, using tools, fire, and so on. And we have built in us, we have knowledge about information, knowledge, we have data about natural hazard and risks. So if we go up in a very high place, we look down, immediately we'll feel dizzy because our senses tells us, oh, it's dangerous and so on. And this was good till the end of the 19th century. From the end of the 19th century, science started to deliver very exact and good information. So we know, we understand that, for example, diseases are caused by bacteria, by viruses, and so on, and we understand things when we can improve them and so on, yes? So we have also many risks that we can manage them today because we understand them scientifically, yes? Real scientifically with evidences and so on, yes? So everything that we know, we can actually manage it, its risk and make it safe. However, we have also things that we don't know enough about them. I call them virtual risk or hazard, yes? And if we don't know what to do, we cannot manage them, yes? So we as society have to invest a lot of resources, time, money, and so on to investigate those problems so we can make them safer. And I will not talk about the unknown unknowns because I don't know if you are familiar with this. We don't know it, and so therefore we cannot do anything about it. So these virtual risks are non-manageable, and we have to understand it. And therefore, if we all are now for the last year, 9 months, 10 months, or whatever, are within the COVID or coronavirus pandemic, and you hear the news in the news, oh, the decision was like this, and then others say the decision is like this. It's so balagan because we do not have enough information about the risk and the hazards, and we have to accumulate it. We have to invest money. Yes, because you remember, if safety is too expensive, try an accident. So we have the Corona accident now, and it costs a lot of money because we didn't invest enough money in understanding such problems. But if we go to your world, yes, also, let's say if we look at the problem of pesticide that the industry is selling and the farmers are using and so on. Is it good? Is it not good? How should we regulate it? We change it all the time. All the bees are dead because of this. And so we don't know actually enough about it. And therefore, it's very hard or difficult or impossible to manage it from a safety point of view. But again, let's go back to the pesticide and to the bees that are dying because of them or not because of them. When we think in a linear way, and this is how our evolution taught us to think in a linear way, we know that accidents are something very tangible. We see two cars crashing, we say it's an accident. We know that the airplane, whatever, fall down because the engines are not working, it's an accident, and so on and so on. So we actually call accident phenomena where the feedback loop is accomplished very fast, and we know the results of something that happened, of a process. But it's not the end of the story. Yes, and of course, it has certain times, so it will take few milliseconds to understand that two cars have done an accident, a crash. But there are also accidents that are hidden, yes? For example, the asbestos problem. It takes about 30 years for people who were exposed to asbestos fibers to get sick. So where is the accident? At the first day, at the first second of being exposed to asbestos, or at the end when the person is sick? But we can understand that these are also accidents, but the feedback loop is accomplishing very, very slowly, yes, or even not accomplished. So maybe the problem with a pesticide, maybe only in 100 or 200 years, people will say, oh, we were so foolish 100 or 200 years ago when we were using pesticide or other things, yes? Or sometimes even unknown. And this idea of hidden accident, I got from a colleague of mine. He's a professor of law, an Israeli, and he's analyzing it. And we know that in the United States, there is something called Innocent Project. And we know today that about 5%, some people say 10% of the people in the United States who are jailed to death or for lifelong in prison because of a major crime, DNA shows that they were not guilty. So they were sitting for many years in prison or even were executed, and nobody knew that it's an accident. So we have also this type of accident. Okay, now again, systems. I don't know how you think about system. We would like to look at them at different view. We are talking about socio-technical system. We are within a socio-technical system. Israel is a socio-technical system. Most of our behavior related to safety is dictated from above, or the parliament, the Knesset, and then the ministries are saying, teaching us or telling us what to do and so on. But these systems have also the lower part of the system. And as I said before, since the beginning of humankind, humanoids and so on, many millions of years, we actually evolved in mechanical systems. And example is this kind of airplane. And then, let's say, over the last 60, 70 years, no, sorry, 120 years, telegraph was the first electromechanical device. It is from the end of the 19th century. We have also electromechanical systems. And in the last 50, 60 years, we have also computerized control systems. What is hardware, software embedded systems, yes? So when we think about system, we think about socio-technical systems that are either mechanical, electromechanical, or software hardware. Now, why is it interesting? Why are we interested in it? Because we look at system as being, as I said before, in control loops, yes? So people who lived or live in a mechanical system, yes, there is an operator, he has some process to control. It can be just hitting with a hammer or with a stone on something, on a nut and break it. But it can be also a very complex mechanical system. But in a mechanical system, we observe directly the process. Yes, and I said before, this we are within this system for many million years. Now, the electromechanical system is just from the end of the 19th century, yes, about 120 years. You can see that in an electromechanical system, we are using sensor to help us, displaying and so on, and we have a synthesized perception. So the system is more complex. And of course, if we go to a hardware software system, we have always a computer in between. If you are driving modern cars from the last few years, they are all controlled by computer. Yes, you hold the steers, but the computer is doing actually most of the work. The same with airplanes, the same with many other systems. And this, it's just 60 years. Yes, now here you see, well, it's very small. The safety model for the mechanical system is so-called the domino effect. I hope you heard about it. I'm not going to explain it. And the domino model or way of thinking came about 100 years ago, 90 years ago. So humankind started to think in relation to safety just 100 years ago, 90 years ago, modeling safety, yes, but of course it's good for a mechanical world. And then it took again, let's say 60 years ago, people developed the so-called Swiss cheese model for safety, yes? Again, I'm not going to elaborate it. It's a little bit more complex, safety model complex, but still it's a linear model. And we have now, we live about for 60 years within this software hardware system, yes, but only 20 or 18 years ago, people started to think about system models for safety. And I will explain it. But before it, if we just from a theoretical point of view, if we look at a mechanical system, at the electromechanical system, and a computerized system, yes, or software hardware system, and we just theorize that we can have failures or flaws in either in the elements or in the pathways of the control or the feedback. So it's purely theory, yes? So you can see that in a mechanical system, we can fail there are 8 possibilities to fail in a very simplified presentation. In electromechanical, we have already 12 possibilities to fail. And in a computerized system, we have 15. So the modern systems, hardware, software, embedded systems, and so on, they are much more efficient, but they are much more prone to problems. We have to understand it. And therefore, system safety science developed over the years. And this is, well, it's too small to, this is the model of that I will talk about, it's thumb. Okay, now, I just said that about 20 years ago, 18 years ago, this system safety model started to develop. But actually already in 82, Kletz, that I hope you know about him, he's one of the pioneers in safety of process industry and so on. He was a Jewish person. He came a few times to Israel, I know about it, but he died. He was very old. And he, in one of his papers, he described an accident, yes, again, this reactor had a kind of exogenic process in it. He got a catalyst that made the reaction to produce heat. And there are some cooling water that cools the system. And one day they decided to computerize it. And there is a computer that with the software controls now the entire system. But the computer is run by software. And the software is written by programmers. And the programmers, if we want them to write a safe software, the requirement should be good for the programming, yes? But they got, because the programmers are just doing what they're told. So they got a requirement that if something happened, leave all control variables as they were and sound an alarm. And this way, the program within this computer that control everything was running for a long time. And then there was a problem, yes, not related directly to this reactor. The gearbox had not enough oil, but the computer did what the program was saying it should do, yes? So it sounded alarm and left everything as it was. It happened that at that time, there was more catalyst in the reactor and very few or very little cooling water, yes? And there was, it was overheated and discharged into the atmosphere and so on. So actually, we describe here an accident with no component failure. There is no failure in nothing. Nothing broke, nothing, yes? But the requirements for the software were wrong because the people who were in contact with the programmers didn't maybe understood well the system, yes? So already in 82, people knew that accidents can happen not only because of failure of a component and so on. Okay, so why we need a new approach to safety? Traditional safety engineering approaches developed for relatively simple mechanical, electrical, mechanical systems. We know today that accidents in complex software intensive systems are changing the nature. They're not the same. We can have accident without any component failure. And also the role of humans in system is changing, yes? Because if the computer is doing the work now, we just have to oversight the computer and not the system itself. So traditional view safety as failure problem or chain of directly related failure events leads to losses. It's not good. But this traditional way forms the basis for more safety engineering and reliability engineering analysis. So I don't know if you have in your department any courses teaching safety, but I'm sure that if they teach safety, they teach one of these, maybe HAZOP, yes, as engineering analysis tools. And also for design in the chemical industry, they use a concept called LOPA, yes, where you have to establish barriers between events or prevent individual component failures, yes, by redundancy, over-design, safety margin, and so on. But all these are traditional, old way to look at accident and systems. So we have a problem. The thinking of the chain on event model is too simple for today's system, yes? And engineering has fundamentally changed in the last 60 years. And we're not going back to mechanical or electromechanical systems. It's finished. Oh, maybe the coronavirus will bring us back, but I don't think so. So accident prevention analysis techniques based on them will have limited useful. We are not saying that not good, but they are limited usefulness. And another thing is that we have to separate, totally separate between safety and reliability. As long as we are looking at component failure as a cause of non-safe, then reliability and safety are strongly connected. But in the modern world, safety and reliability are not connected. We can have systems that are very, very reliable, but are not safe, or opposite. They can be very, very safe, but not reliable at all. And well, we have to remember it. So again, a kind of a historical view, yes, starting from the beginning of the 20th century, we can see the model of thinking model, root cause, domino, FMEA, HAZOP, fault tree, and so on and so on. Yes, there are linear models, or some of them we call it composed linear models, and only about 18 years ago, two lecturers started actually systemic models. One of them is STAMP, developed in first time published in 2004, 16 years ago, but of course she started a little bit earlier, by Nancy Leveson from MIT. And the other model is called FRAM by Danish scientist. He is not a safety, he's a psychologist, because many people in safety are coming from the human perspective of safety. Yes, so all these assume that accident caused by component failure, and they are just not good. Not good. Again, they can deliver results, but they're not good enough for our modern times. So if we have all this, we can wrap it together, and therefore the logical conclusion is, yes, that we go to, because I think STAMP is better than FRAM. I will not explain now why. This is my impression, but there are also people in the world who are using FRAM. And if the STAMP is a model and it has two tools, and well, I will talk about it. But what is safety? Safety, we say safety is just absence of any losses. Yes? So we use in everyday talking, we use accident, mishap, loss, disaster. They are all the same thing. We are referring to some losses. And what are the losses? Any undesired and unplanned event that result in a loss, and any that matters to the stakeholders. So one stakeholder can say that if someone is dead, it's a loss, but also property damage, environmental pollution, negative business impact, damage to reputation, mission loss, product launch delay, legal entanglement, bankruptcy, and so on. And as I said before, it includes also involuntary and intentional losses, security. And now we are approaching more and more to STAMP, and STAMP says the same. Yes, innovative safety paradigms and non-probabilistic. STAMP is non-probabilistic compared to other tools maybe, to achieve freedom from unacceptable loss event. And you see the list, it's the same as in the slide before. Okay, so now I will talk about STAMP, but because you probably never heard about STAMP, so you say, oh, this Daniel Hartmann from the safety engineering unit, he's a weirdo person. He invents something and he tried to convince us. So therefore, I first will show you the activities, yes? So there were, a few months ago, we had a big virtual workshop using Zoom, and there were more than 2,500 people registered and involved in the workshop. And you can see that they are from all kind of discipline, all kind of industries, also from academia, not from Israel. From Israel, only one, sorry. Yes, so you can see that there are different industries. Because Nancy Leveson is in MIT at the aeronautical department, she has, and she started by working with NASA and so on. So she has a strong inclination to aviation and so on. But you can see that many industries are involved and also departments in universities. I use this slide to show you that I myself and my students, because as I said before, I'm a multidisciplinary person, and the model is good for all kind of engineering, yes? So our students, my students in my supervision in the master thesis, they were dealing with all these different industries and problems, yes? So it's there. And here just few lists, yes, about all the countries that were involved in this meeting. From Israel, again, only me. You can see here all the countries where STAMP is already used. Israel, again, sorry, it's only me. And here you have a map with all kinds of industries all over the world. And Ben-Gurion is in the middle here. It's, again, only me. So I'm not a crazy person trying to convince you to understand that safety science and especially STAMP are there, but the world know about it already now for 10, 15 years. Okay, again, STAMP, the traditional way to do safety is good, yes, but STAMP is much better. So if the tools, STAMP is a model and STAMP has tools, and I will talk about it. So if the traditional analysis can, the tools are strong, again, of course, it is a scheme. This way, STAMP-based hazard analysis is much wider, much stronger, the tools. And therefore, they can deliver scenarios, because you remember, we are interested in safety guided design. So we actually have the system only in a conceptual way, but we can already find, even if we have only concept in our hand, yes, and the functionality of the new system that we want to design, we can find many scenarios how the system theoretically can fail before we even have it, yes? And just again, to convince you, I will show you now 3 slides. These are the product of my students analyzing accidents. And you can see that this is the results of my student. And this is, in this case, is a chemical safety board. Again, you are chemical engineering. I don't know how many of you know about chemical safety board. Chemical safety board, it's a federal institution in the United States. They are responsible to analyze all major accidents or disaster within the process industry. They have excellent website, excellent reports analyzing various accidents. I mean, only this slide well, demands extra lecture for itself. But still, although they are very good and they employ a lot of people, skilled people and so on, we found And we didn't have, we relied just on their results. We found 56% more results than they found. But if we go, and this was, by the way, sorry, this was a disaster or accident in a refinery in the United States where a few people were killed because explosion of the heat, the heat exchanger or heat tubes. Another work of study of another student is a radiation accident happened in Sorek, in the Mamag, by Yavne, in the nuclear research facility. And over there, we found 3 times more outcomes than the official results, yes? And again, we study not only the physical level, we go up to the regulation and so on. By the way, in the previous accident or disaster, one of the findings was that the standards were just wrong, and everybody knew about that the standards are wrong for 40 years, but nobody cared, and nobody changed the regulation. And again, a few years ago, we had near Dimona or in Dimona, we had a train colliding with another train or wagons of a train. The Brom incident, lucky, we were very lucky. It didn't become, nobody was killed there. And another student of mine, he found almost 6 times more results using a tool of the STAMP model than the official results. And especially you can see that we look also in the upper level of what I said we called before socio-technical system. And I will try to explain, but I have no time. So now I'm running out of time. So what is this STAMP model? It just said, instead of preventing failures, we have to enforce safety constraint on system behavior. Now, sorry, I didn't see that the time is running, so yes. And it's based on system theory, hierarchical functional safety control structure, process model, and safety constraint. And sorry, well, I'll not read everything, but I said most of the things I said already. And it focused on the entire complex socio-technical system. We have a system which has hierarchy in itself. Yes, it's a functional safety hierarchy. And we do everything top down, the analysis and so on. And then we have the model, again, it says accidents are caused by inadequate control. And on top of this model, we have a method called STPA, which is a hazard analysis. We are doing hazard analysis and not risk analysis, because in risk, we have to think in probabilities. But actually, we very seldom know about the probabilities. And if we go to computer programs, there is no probability of failure. So therefore we don't, and Nancy Leveson has a PhD in mathematics and computer science. So it's not because she hates mathematics. And STPA just asks, how do we find inadequate control in a system? Of course, these are just words. I have no time to explain further. And then we have another tool, which is accident analysis. And in an accident analysis, we just ask ourselves, how do we find inadequate control that caused the accidents? Yes. So actually, the same model has a reactive tool to look at accidents, disaster, or whatever you call them, and a proactive tool that we want to have it as a safety guided design, as I told you before. Now, we took many ideas from systems engineering. I don't know if you know it or not, but from this year, this semester at our university, finally, we started to have a systems engineering master thesis. In the Technion, they have it almost for 30 years. You cannot work today in the industry without system engineering. So we take the life cycle from the system engineering, thinking in life cycle, from control theory, we take the idea that everything should be composed regarding safety in control loops or closed control loop structure, yes, where we have a controller, we have actuator, we have hazardous process, we have sensor, and so on. And of course, this control loop should work all the time, so we can control the hazardous process. Of course, this is just an idea of what we have in our mind, yes? And of course, the controller needs to know what are the goal of the system that he is controlling. And of course, he needs to have a model of the controlled process. And we saw in the Klets example of the accident that actually the controller did not have the model of the process, and therefore the requirement for the software were not good enough. And of course, we have a control action and we have a feedback. I will skip because, and just give you an example. Let's take electric kettle. Yes, we can model it. It's a very, very high level modeling. It's abstraction of something, yes? Of course, we go afterwards deeper into everything, deeper and deeper and deeper. Yes, so we have a person, he wants coffee or tea. He has an automatic, the controller, the next second controller is the automatic boiler. It has a hazardous process reaching request temperature. There's a sensor and so on, yes? And this is, we know if we want to construct, we want to design an electric kettle, we know this, but we know that this can have control problems in different, it can have control problems here, 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 here. And actually, already 15 years ago, Nancy Leveson has a list of potential generic control and feedback flows, yes? But we are much further today, yes? Where everything theoretically, before we, as I said before, when we write down the requirement for the system, we know that theoretically all this can go wrong, and we can do things in the design so that we can control these problems, and that they will not happen. And I will skip, sorry. Okay, but again, we start now to build these control loops, and we get a socio-technical system, yes? So I showed you the kettle, the water kettle here, but actually there is someone managing it. It's a person, but when he bought it, of course, there's regulation on this water kettle, but it's the same, can be driving a car, you driving a car, but of course you're driving a car in a safe way because all the system told you how to drive the car, yes? So there is a socio-technical system dictating the safety at the lower part of the technical system, yes? And of course it should work all the time. And most of the accidents that we are aware of happen below, and everybody who lives in Israel knows that the Shin Gimel is always Hashem, yes, but of course it's the old linear thinking, yes, that down below they are responsible for the problems, and they don't think that up above their responsibility. But of course you can now go deeper and put more names into it, yes. So of course you have the level of the legislation and the higher first legislation, second legislation, regulation, company, and so on and so on. And of course, there are the control actions that goes down and the feedback that go up. And the model is from the end of the 20th century. Leveson took it, and she said actually that we need two control structures, because if, for example, we want to have a transportation by air, yes? So we have a control structure for the companies that construct airplanes. And then once the airplane is constructed in a safe way, going through the whole socio-technical system that is responsible for it, then they will sell it to companies that operate it. So we have, and it's a different structure. So therefore, we have to separate between them. Yes. So again, here you see evolution. First, we had the socio-technical system, and then Nancy Leveson said we have a system development control structure, the system operation control structure. And then again, me, myself, and my student, we found out that they need a third control structure for response. Safety of the response. I don't know if you probably know that most people in the Chernobyl accident or disaster, they died not in the operation of the power plant, but in the response, in the rescue efforts. The same is also for the 9/11. Many people died during the response because the response was not safe enough, or they were not thinking about the need for safety. Again, I showed you very linear models. Of course, in reality, the structure can be much more complex. Yes, we have many different processes that we have to control and so on. And we have hierarchy of different controllers. And we say that safety is emergent property. Safety can be related only to the entire system and not to parts of it and so on. Okay, and now we have the methods. STPA, as you remember, is the hazard analysis method. It has 4 steps. Again, we don't have time. We define the purpose of the analysis. Yes, we start top down. We start very high level, and then we go deeper and deeper into the different loops, control loops. And in a complex system, you can have hundreds of control loops. And you have to look theoretically, yes, in the design and to analyze all the control loops. And then, of course, we have to build the control structure. And I think my time is almost over. So I just show you the control structure, 3 control structure related to the train accident, the bromine train accident in Dimona. So this is for the development. And because most of the equipment related to rails in Israel is bought from abroad, then we have also to go and look at abroad, how they regulate the safety of the rails, the wagons, the isotanks, and so on and so forth. And then, of course, the Israeli and how they collect it. And all these are these control loops that we have to analyze and to understand them. And this now the operation of the trains in Israel. And of course, you can see all the complexity in it and how they talk to each other, if they talk, and so on. And here is the response control structure is different. Yes, you have police and military and environmental ministry and so on, and hospitals, and very complex. And I think I will finish by it. Just a student of mine, she finished a month ago. She analyzed the safety, she started to analyze the safety of, and you are chemical engineering, of safety of laboratories, yes, at universities, academic institutions, and it's so complex. She needed half a year, and it's her specialty. She's working in safety. It took her half a year to understand who the regulation, who is telling whom what to do in regarding safety of laboratories, academic laboratories, and so on, research, and so on. Yes, so it's so complex. And of course, you have to go each of these control loops and analyze it and understand it and so on. Okay, I think I finish here. I want to be somehow in the time frame. There is so much to say and to talk about. So if you have some questions or remarks, I will stop here.
Toda rabba, Daniel. Thank you very much. Very interesting talk. I think many of us will relate to the last part with the laboratory safety and who tells who what to do and how is that related to our daily work. We have time for one quick question.
By the way, the accident where the professor was killed at the Technion, it was after we started to look at this problem, yes? So it was not a trigger for our work. The trigger was actually a dispute in the university regarding the safety, who is responsible for the safety. So we have some good insight, I think.
Any quick question?
Yes.
Okay, so
I have a question. Maybe if you can just give us like a quick insight from the last study that you did about like a rule of thumb that we should know of about the lab safety or hazards. Like what was the conclusion of
the rule of thumb is that, again, it's very similar to the corona problem. It's a balagan. The system is not coordinated. One part of the system does not know what another part of the system is doing. Who is responsible? So there are so many. I mean, we just started to feel it because again, in our unit, people are doing master thesis and final project. I don't know if you have this. And she was doing just a final project. So she invested a lot of time and efforts just to understand that there is a big balagan in the system. And she started to organize it. So
a lack of order and communication maybe are the things
but
to
again,
tackle first?
We can put the finger and we can say this is this, and so it's not just saying it's a balagan. We can show it. Yes, we can show actually with one graph. This is a very graphical method. For example, I can show you just using this graph or this picture. I can explain a crash of 2 airplanes that happened 30 years ago and so on. Just with one graph and its control structure, I can show you where the weaknesses of the system are. Yes, and again, this is about 100 people were killed in this accident. Yes, and there was no element, nothing failed. Nothing failed in this accident, just the communication. Yes, so it's what your question. Sorry, I apologize if it sounds that your question is coming from a linear thinking, yes? So from a linear thinking, you look for the root cause. Okay, what is the problem? We take a hammer and we hit.
No, I'm asking about the weak links that you recognize.
The structure is weak. The legislation is weak. The Chakika Rashid, the primary legislation, the secondary legislation. The management doesn't understand actually the matter and so on and so forth, yes? So the weaknesses are all over.
Okay, thank you.
okay, thank you, Daniel.
Yeah. Okay.